Acción.
Hi, I'm Diego, and today I'm with Ana and Ricardo, and we're gonna talk about the Lloyd's mirror. So first, we're gonna do a quick review on our last presentation, which was a Young interferometer, where we define interference as an effect due to the principle of superposition, where two waves superimpose at some point be in the space, and they either generate a bigger wave or a smaller wave, or slightly bigger or slightly smaller. In terms of intensity, it is just the intensity associated to the first wave, the intensity associated to the second wave, and then some additional term that we're going to define it as the interference term. This is the term that we want to study when we analyze interferometers, since it's going to give us a variation of this sum of intensities. This term can be expressed in terms of the fields of the waves that superimpose, and is this expression over here, where delta is just the phase difference of the waves. Now, if we assume if each that its source emits the same wave number, then we can express delta in terms of the optical path difference. So now we just want to know at which points the intensity is maximum or minimum, which just means when this cosine is going to be either 0 or -1. So then this is the condition for cosine b to 1. So then this is the condition of the optical length for maximum intensity, and this is for minimum intensity. However, notice that this is for any given interferometer. So the big question that we want to ask when we analyze an interferometer is just what is the difference in the optical path.
Okay, so the interferometer that we are going to be analyzing in this presentation is the Lloyd's mirror. Here we have a diagram of the geometry of the interferometer. As you can see, we have here a source S, which emits light in such a way that some of the light reaches the point P at the screen, and some other part of the light gets reflected here in the mirror. This light that gets reflected seems to be coming from a virtual source S prime, which is at a distance d from the original source. And these two sources are at a distance d from the viewing screen. But as you can see, these two sources act as analogs for the slits in the Jones interferometer. So the geometrical analysis for the path difference that we are going to apply is pretty much the same as in the Jones experiment. But the only thing that we have to take into consideration is this phase shift of pi that gets from this light that it gets reflected here, which gets this phase shift of pi, and that we are going to take into consideration for the interference conditions. The materials that we employed for this experiment are a Pasco microwave optic system, which basically consists of a wave transmitter, a receiver. We connected here a multimeter to the receiver, and this is the ionometer plate, and this is a reflector.
We place the ionometer, the transmitter and the receiver at the same distance from the ionometer, and we place the reflector at the first minimum that the multimeter measured, and from there we move it backward to obtain 10 measurements of minimums. We analyzed this experiment to obtain the optical path difference from this diagram, where the point A is the transmitter, the point C is the receiver, and B is the reflector. So we have the optical path difference would be the line between A and B plus the line from B to C minus the two distances from A to C, well, the ionometer. But as I said, the distance from the transmitter and the receiver to the ionometer are the same. So D1 and D2 are considered D. So in result, we have that these two triangles are similar So A and B is the same distance to B and C. And we have that the lines A and B are the hypotenuse from these two distances. So we get this expression from the for the optical path difference.
Here we present two tables which contain the distance h, which is the distance that the reflector was placed in such a way that it indicated a minimum of interference. And these two tables corresponds to this distance d each. And this formula here is the one that we use to calculate the optical path difference. And this formula here is the one that we use to propagate the error.
So for the first series of H, we calculated a different path, optical path length for each H, with each associated error with the equation from before. And we evaluated for all the m plus 1/2, which is the equation of minimum condition. And then with this data, we made a plot in Python. These red lines are the error. And we make a line fit on Python, which will give us this slope, which from this equation over here, we can notice that it should be the same as lambda. So this is the experimental lambda calculated with this respective error. So when we compare with the theoretical wavelength, we get that we have a 5.35% of error.
We applied the same method for the second series, obtaining these values of the delta L and comparing it with. We also uploaded the same graph, and using a linear fit from Python, we obtained the slope that from the interference condition should be equal to lambda. And comparing it with the theoretical value of lambda, we get an error of 5.52%.
So as we could see, both of the errors obtained were, well, technically small. So we can say that the methodology used to obtain those values of the wavelength were efficient, and therefore all results are good. The question that we were trying to answer while we were doing the experiment was, what is the advantage in having the effective transmission and reception points equidistant from the center of the DP plate in this experiment? And well, because of the diagram of the top view of the experiment that my partner Ricardo showed you, we can say that the distance D and D2 are equal, and therefore the triangles were similar, and so we could express those distances as only one, the distance c, and therefore that calculation made the calculations for the optical path difference very easy, and it also made easier calculating the error propagation of the data obtained. And as my partner is going to show you, the calculation gets difficult when you don't have this condition of equidistance.
If we don't take into account this advantage of that D1 is equal to D2, we get now this expression from the same optical path difference, that AB plus BC minus the two distances should be the path difference. We now have that the AB is the hypotenuse of D1 and H, and BC is the hypotenuse of H and D2. So we now get this expression of delta L. This is a more complicated expression than the one before. And also to obtain the errors of this expression would be more difficult, because we now would have to take into account the error of D1, H, and D2.
So a nice application for the Lloyd's mirror is this model over here that is used to analyze the sound contamination underwater. So if we think a boat is making noise underwater, saying this sound source, we can model the surface of the sea as a flat mirror, which will generate a reflection here, which similar to the Lloyd mirror, it will generate a virtual source, which of course will generate some interference at some point. This interference is measured in terms of the sea pressure, sound pressure level, which is what generates this underwater noise. So then animals like manatees or dolphins that base their location by a geolocation, sometimes they get like disorientated and some accident happens when this animal crashes with the boats. Or this sometimes for submarines can generate noise when reading with radars. So then this useful model is used to study this noise contamination underwater in order to improve, uh, to reduce this contamination. So in conclusion, the equidistance was a really huge advantage of this experiment, that since it will reduce our calculations. And when we talk about the measurement that we made, we did find really, really good approximations of the wavelength, since we just have some errors of 5.35 and 5.52, respectively. So interference was, the interference condition was proved, and the wavelength was successfully calculated. Thank you.
Thank you.